So I wanted to talk about rotations. These are rotations of rigid objects around the fixed axis. So like a wheel or disc or anything that has a, it's rigid, it has a fixed axis of rotation. Okay, so let's think about just typical wheel. Okay, let's say it's rotating this way. So this is a wheel spinning. I'm not talking about translation, so we're going to get to that, but where it's rolling, or which I would say rolling, it's just stationary and it's spinning. So we need to come up with a way to deal with this type of motion. And I asked the question, if this thing is spinning, let's take a point right here and maybe a point right here. These 2 points are not traveling at the same velocity. We already know that. We talked about that with uniform circular motion. Okay? These points this point is traveling faster than this point. Okay, if you think about that tangential velocity. Also, it's traveling farther. This point is traveling farther than this point. I mean, that's why it's traveling faster. It has to go farther to make one revolution. But all the points on a rigid body, they do have, when it's in rotation, they do have something in common. They all pass through the same angle. So these 2 points, let's say we start here, call this theta initial, and you go over here, okay, and this is theta final. Then it's awful. I'll put a new center. All the points have traveled through the same bit of angle, delta theta. All right. So this is the idea of angular displacement. This is going to be 1D motion, just like we had the first part of the semester. That dimension is angle. Angle will be in radians, okay? And remember that the relationship between distance, angle, and radius is S. That's the distance. So this drawing's not great. So that distance S is equal to, the way I've drawn it, R delta theta. I guess that would be delta S. Okay. All right. Typically you just write S is R theta, where the understanding is this is some angle theta, this is at some radius R, and that would be the distance. Angle is defined as the ratio of arc length to radius. Okay? Angle doesn't have a unit. We call it radians, but it's actually unitless. These both have units of meters. But we understand that we're talking about a rotation or some angle, and that ratio of arc length to radius is angle in radians. So just like we did with 1D motion, where we had delta x, and we called it the displacement, we have the angular displacement. Angular displacement is delta theta, and that's theta final minus theta initial. Just, you replace, wherever you had an x, you replace it with theta. That was, when we had 1D motion, this was delta x final minus x initial. Now it's theta final minus theta initial. And just like we did with 1D, linear motion, you pick where your theta initial is. What do you want to call theta initial? Do you want to call it here on the x-axis like we always do, or some other place, it doesn't matter. Then we can define angular velocity. Okay, so angular velocity is, we give it the letter that's not W, that's omega. Omega is delta theta divided by delta t. That would be the average angular velocity. It's the rate of change of angle. The instantaneous, well, this is average. The instantaneous, just like always, is d theta dt. Just like we had with x. That was delta x divided by delta t and dx dt. Now it's theta. All right? That leads us into an object that's rotating and speeding up, or rotating and slowing down. You have angular acceleration. Angular acceleration is alpha, and it's equal to d omega. Well, let me write it as the average. And for us, we're going to have constant acceleration, just like we did with linear motion. So alpha is delta omega divided by delta t. It's the rate of change of angular velocity. And that's also equal to d omega dt. That's equal to the second derivative, d dt of d theta dt. I can't write this low. D omega dt is equal to d dt of d theta dt. It's a second derivative of the displacement. Second time derivative. Okay? So, we're going to have all those equations that we had before with objects that are rotating. Those ones we had before with linear motion. Okay? They have omega is equal to omega initial, or call this omega final. I don't know what the notation is in Survey, but you're familiar enough now with this notation, I think, to understand what I'm saying. Omega initial plus alpha t. And theta final, or maybe just written as theta, is equal to theta initial plus omega initial t plus 1/2 alpha t squared. Okay? Now you can use that other one that we had with velocities, like v squared minus v initial squared is equal, you can use that one as well. All right? By the way, alpha and omega can be positive or negative. Here's the way we typically define the vector. The angular displacement is a vector, the angular acceleration is a vector, and the angular velocity is a vector. It's not a typical vector in the sense like you think of, you know, delta x is in that direction or v is in that direction. If you have an object, let's say it's rotating this way with some angular velocity omega, you put your fingers in the direction of rotation and your thumb gives you the direction of the vector. If you think back on what we did with torque, when we did that in lab, I know we haven't talked about it in class, but in lab we talked about torque. You put your fingers in the direction of the force, okay, or the intended rotation, or your thumb gives you the direction of the torque. Same way here, if that's displacement is in this direction, that it's this right-hand rule, your thumb's in the direction of the vector that represents that. So that gives you a way where, let's say this is spinning this way and it's speeding up. So omega's in that direction and alpha. That would be a positive omega and a positive alpha. If it's slowing down, say alpha is in this direction, then that gives you a negative alpha and a positive omega. Typically, just the convention is that counterclockwise rotations are positive, clockwise rotations are negative. Okay? Doesn't have to be. Okay, it's just like you can make the x-axis positive that way and negative that way. It's up to you. But the typical convention is if you're looking at the object rotating, counterclockwise rotations are positive, clockwise are negative. Just like the unit circle. As you're going from that positive x-axis and you're going this way, that's a positive bit of angle. Okay? So angular displacement, angular velocity, angular acceleration are vectors. They have a direction and a magnitude. Okay, so let's look at a typical type problem. Let's say a wheel. A wheel has an angular velocity of 15 radians per second and an angular acceleration of 2 radians. Oh, I didn't give you the units for. Okay, so angular displacement, delta theta is radians. I did mention that. Omega is radian. I mean, this is, I think, what you would expect. Omega is radians per second, and alpha is radians per second. So, radians per second squared. Okay. So a wheel has an angular velocity of 15 radians per second and an angular acceleration of 2 radians per second. Through, it's a weird through. Through what angle? I'm making it super simple. What angle does the wheel travel or wheel rotate in 5 seconds? Okay. So this thing's rotating. Not only is it rotating, I'm going to get rid of this. It's speeding up. Something is accelerating it. So it's rotating. Omega initial is equal to 15 radians per second. Okay. Theta initial, just let that equal 0. And alpha is equal to 2 radians per second squared. So alpha is in this direction as well. If it were slowing down, alpha would be this way. I mean, I could make it that way, but... So, we'll just use those 1D motion equations. Omega plays the role of velocity. Alpha plays the role of acceleration. So if we want to know the angle, theta final is equal to theta initial plus omega initial t plus 1/2 alpha t squared. Okay? theta initial 0, so theta final, this would be the angle through which it rotated. Omega initial is 15 radians per second times 5 seconds plus 1/2. Alpha is 2 radians per second. I'm bleeding over here into my picture. 2 radians per second. 2 radians per second squared. And then t squared, so 5 seconds squared, and this is 75, the 2's cancel, 25, so 100 radians. Nice and simple. Okay. You can calculate the angular velocity after 5 seconds, because the angular velocity, omega final, is equal to omega initial plus alpha t. Okay, so this would be equal to 15 radians per second plus 2 radians per second squared times 5 seconds. So this is equal to, what's that, 25 radians per second. It's just 1D motion. And that D is angle. Angular displacement, angular velocity, angular acceleration. Any questions on that? Got a gnat in here. I hate gnats. Okay. Say a couple other things about this that are related to the uniform circular motion that we did previously. Here's an object. Let's say there's some wheel. This distance is r. Okay. It's rotating. There is a tangential velocity in this direction. You all know that there is a centripetal acceleration in this direction. Okay? And we'll also talk about a tangential acceleration, which when we did uniform circular motion, we didn't have that tangential acceleration because the object was always rotating at a uniform speed. But now, since we have this angular acceleration, these particles that are rotating can also be speeding up or slowing down. So I'll draw in a, you see if I can fit it in here. Here's a tangential acceleration. Okay. So for the V tangential, that is just ds dt, right? That's that arc length, the change in arc length divided by the change in time. That's the tangential acceleration. And S is equal to r theta. So if I put this together, you get V tangential is equal to d dt of r theta. We're not allowing r to change. So this is r d theta dt, which is simply r omega. It's super simple. If you want to know the tangential velocity of a particle as it's going around, it's just its radius from the axis of rotation times the angular velocity. Think about units. That makes sense, right? This is in radians per second. This is in meters. Radians are, I don't know if I want to say a made-up unit, but they're unitless. So this is meters per second. The tangential velocity is r omega. Okay. What about the centripetal acceleration? Well, we know from what we did in the past, that's v squared over r, right? That's that tangential velocity squared divided by r. So tangential velocity is r omega. This is r squared, omega squared, divided by r, and it is equal to r omega squared. Okay? So the centripetal acceleration is r omega squared. Now, the tangential acceleration, so if this object has an angular acceleration, it's speeding up, it's spinning, and it's getting faster and faster and faster, then this point not only has a centripetal acceleration in this direction, it's speeding up this way. Okay? So that's the second derivative of the tangential. No, that's the first derivative of the tangential velocity. So you get d dt of v tangential, and that's equal to r, which we're not allowing that to change, d omega dt, and that's equal to r alpha, which makes perfect sense. You have an angular acceleration alpha, you multiply by r, whatever radius you're at, that gives you the acceleration of that point. Okay? These two are easy. This one you have to do a little work, but you get an r omega squared.